All right, welcome everyone for joining us today. This is a joint webinar with C-Motive Technologies and the Wisconsin Sustainable Business Council. We're going to be talking about leveraging motor technology to save on energy costs and emissions. So this is a fun opportunity for those of you who are interested in energy savings and greenhouse gas savings to get a sneak peek at what C-Motive, which is a startup in Madison, has been up to. They're sort of the star of the show today. I'm just going to do a very quick overview of who WSBC is for those of you who are less familiar with us, and then I'm going to turn it over to them. Let's get started. So the Wisconsin Sustainable Business Council's mission is to advance sustainable principles and practices forward through the power of business. So we are owned and operated by WMEP Manufacturing Solutions, and our tagline is here, educate, measure, improve, and connect. So really, this is the way that we support businesses in their sustainability journey. So it's a lot about education. We do monthly, sometimes more than monthly webinars. We have a platform that members can access with a lot of resources in it. We host peer-to-peer groups, working groups, that sort of thing. We also have a Green Masters program, which our new program is going to be launching later this month. So it's a very exciting time for us. So that is a free tool to our members. We also facilitate connections. So this sort of thing with both members and others working in sustainability. We sort of help facilitate making those connections so you can all meet your sustainability goals or advance those goals. Again, we also help work on showcasing sustainability success stories in Wisconsin and beyond. I just wanted to share a few upcoming events we have. We have a member meet and greet. This is virtual sort of networking where you get to meet and chat with other members on April 19th. We are officially launching our Green Masters program to members on April 26th at noon. So join us for a demo of that new platform, and we will be launching it to the public then in May. Manufacturing Matters is WMEP's premier conference. That's coming up April 27th. Our next webinar in May is about sustainability management program basics. So this is really about kind of data collection, setting up data, how to create normalization metrics, how to really get the basics of your program up and running. And then we will have an information session in May about membership if you're interested in learning more. You can find all of this information on our website at wisconsinsustainability.com. And if you're looking for events, that's upcoming events. So last but not least, I invite you, if you're not a member, to consider joining. It's a great way to continue to have support on your sustainability journey. All right, so without further ado, I'm going to stop sharing and hand it over to Matt, who is here to share great information about what C-Motive is up to. Welcome, Matt.
Awesome. Thank you, Jesse. Appreciate it so much. Just make sure I've got everything. So you can see slides and you can see me, hear me. That's all. That's perfect.
See you, I can hear you, and the slides look great.
Awesome. Well, again, thanks for having us. Just as a bit of background, well, just to start off with, we've got a number of slides here. The point of what we're trying to do today is just trying to talk about motors in general. You know, maybe something you've never thought about in the past, maybe it is something you've thought about, and just how much motors can actually contribute to both cost savings and sustainability goals. I am happy to answer questions along the way as well. So what I don't want to do is just talk at my computer screen for 20 or 30 or 40 minutes or however long. So whether you want to just like pipe up and yell or raise your hand on Zoom or put something in the chat, I'm happy to stop as we go along and like explain in detail, go back to certain things. So please, we do want this to be, you know, educational and certainly not at all a sales pitch. So we want to make sure that people are getting, you know, answers to the questions that they may have. So again, just real quick introduction. So it's very nice to meet everybody. My name is Matt Maroon. I'm the CEO of C-Motive Technologies. I've been here for just over 3 years now. Just a little bit of background. So I have a degree a long time ago in engineering. Turns out I wasn't a very good engineer, which is why I do what I do now, which is give webinars and do sales stuff. We also have Rachel Hoppy on the line. Rachel's our marketing and partner relations manager. So putting together all of this information, finding these opportunities, and then she also is responsible for engaging with people that are interested in learning more. So again, if you have questions, whether it's now or later, please feel free to email either of us, and we'd be happy to just give more information. So before I go into some background on motors in general, just real quick on who C-Motive Technologies is. So we are a venture-backed startup company located in Middleton, Wisconsin, so just on the edge, the western side of Madison. We've been WSBC members for just over a year now. We joined because a lot of what we do is focused, not just our products focus on sustainability, but also for ourselves. We want to make sure that we're putting the right practices in place, even at this stage of the company, that will scale with us going forward. We're still relatively small, so a team of 16 people. Everybody, with the exception of one, is located right here in Madison or Middleton, Wisconsin. So very, very Wisconsin focused. And the reason that we are here is because this technology was originally developed by our two co-founders while they were doing their doctorate work in electrical engineering at UW-Madison. So our two co-founders, Justin Reed, who's our Chief Technology Officer, and Dan Ludis, our Chief Science Officer, we're always interested in motors and efficiency. And when I get to more about what we're doing at the end of this deck, you'll see a little bit more on what they were able to develop. So just taking a step back from motors, one of the things that I've been interested about with our engagement with the WSBC, as well as attending other sustainability conferences and talking to sustainability directors, is this constant push and pull that you seem to find between people that are looking to save on carbon emissions or embodied carbon, but also not necessarily in a position where they can afford to pay more to implement those sustainability solutions. A lot of what we hear in other webinars and conferences is really about other aspects that are more notable for sustainability. So adding solar to the roof or buying wind RECs, implementing recycling programs, looking at where raw materials are coming for, overall building efficiency programs. All of these are great ways to take a step towards sustainability. All of these will help reduce emissions. Not all of these are the best way to save money right off the bat. Certainly something like adding a bunch of solar to the roof of your building is going to pay off in the long run, significant amount of CapEx up front. So it's always hard to figure out what is the best way to accomplish both of these goals. And the one thing that often just gets overlooked is just energy efficiency in general. And energy efficiency doesn't have to be this massive program where you're changing out all of your HVAC in your facility. It can be much smaller things that can deliver a significant difference to the energy used by your facility, and therefore your utility bill and the avoided carbon emissions from there. Lighting is a perfect example. So 10, 15 years ago, there was a big push to move from incandescent light bulbs to compact fluorescent bulbs, and then eventually to LED light bulbs. Who would have ever thought that lighting would have this much of an impact? But when you actually look at the numbers, that incandescent light bulb that many of us grew up with, you put 100 watts of electrical power into it, and of that 100 watts, only 2% of it actually went to generating light. The other 98% was burnt off as heat. For the equivalent amount of lighting, you can now buy from the corner hardware store a pack of LED light bulbs that cost roughly the same, only need 6 watts of electrical power to generate the same amount of light, last 50 times longer, and don't generate the same amount of heat. And when you look at changing out, from incandescent light bulbs to LED light bulbs, this has been a 75 to 80% savings, just like that, for people and for companies that have made this move over the past decade or so. Similarly, motors are one of those things that we've all taken for granted for decades and decades. They're an essential part of life. And in fact, they are so much of a part of life that over 50% of the world's electricity consumption goes into electric motors. These are examples of things that I have personally touched just this morning that have dealt with a motor. So my coffee grinder, the electric motor in my Prius, my furnace, unfortunately, the furnace was running this morning because it was only 20 degrees outside, as well as the fan on my laptop. Where if you're sitting at home or if you're sitting in the office, there are probably 20 to 30 motors that are within a 50-foot radius of where you're sitting, and they are spinning constantly. In an industrial facility setting, this is feedback that we've heard from customers, is that the amount of electricity going into motors can be as high as 75%. So if you are operating a logistics facility where you have, maybe miles of conveyor belts, everyone has air handling systems with large fans, pumps, compressors, robotics. When you really take a step back and look at all of the motors that are running inside of a facility, you can see just how much electricity is going into those machines just to keep operations running. So now that we know that motors are an essential part of life, they're one of those things that has been taken for granted for so long. What actually is a motor? In its simplest definition, a motor is nothing more than an energy conversion device. You put electricity into a motor and you get mechanical power and torque or twisting force out of it. Motors are all sized differently. They have different configurations on the inside, but again, fundamentally, this is what they do. You need to move something, you only have electricity, you use a motor to do that conversion between electricity and motion. And what they're comprised of predominantly is copper, electrical steel, and permanent magnets. There are multiple different types of motors. And for those of you that have spec'd motors out before or have an interest in this might know that there's a difference between an induction motor and a permanent magnet motor or a switch reluctance machine. But fundamentally, what all of these machines rely on is creating a magnetic field in order to do that energy conversion from electricity to mechanical power. In this case, what you see up here in the upper right-hand corner of the slide, this is the inner section of a motor. This is the rotor or the rotating section. And you can see all of those copper windings. And so what happens inside of this machine is that as you put electricity into it, that electricity flows through those hundreds and hundreds and even thousands of copper windings. That creates a magnetic field. That magnetic field then interacts with another magnetic field in order to impart motion. So the example that, again, not being a very good engineer myself, this is the example that I like to use. It makes sense to me. So when you were in grade school, elementary school, and you went to the science fair, there was always someone that did this experiment where you took a nail or a bolt, you wrap a bunch of copper around it, connect it to a battery, and you create a magnet. And it's because that electrical flow through the copper winding is what creates a magnetic field. This is a simple experiment, but it is the fundamental force that powers 99.9% of motors that are in the marketplace right now. The downside of using magnetism in order to create that energy conversion is that anytime you pass electricity through copper winding, you also create heat. It is just a law of nature that anytime electric current flows through something, you have resistive losses. And in motors that we all take for granted today, heat is actually the largest cause of wasted energy, the largest source of efficiency loss, and is also the leading factor for why motors burn out too early. So if you undersize a motor, you try to pass too much current through it, you try to push too much torque through it, you're going to literally burn the motor out. You're going to create such a high heat inside the machine that you're going to demagnetize magnets, you're going to melt insulation around wires. This is the problem. This is the problem that engineers have been trying to solve for decades. How do I continue to create more efficient motors without generating so much heat? Another aspect of just kind of motors in general that you may not think about often is that not every single motor is sized for every single application. And this may seem intuitive, but in this example and for the rest of this presentation, we're going to focus on a machine of this size. So this is a standard off-the-shelf 1 horsepower motor. Spins natively at about 1800 or 2000 RPMs, and it creates 4 Newton meters of torque, or 4 Newton meters of twisting force. So 2 applications we're gonna center on. One, kind of material conveyance, conveyor belts, vertical lifting apparatuses, that sort of thing. So a typical conveyor belt needs its motor to spin at 200 RPMs. You had a motor spinning a conveyor belt at 1800 RPMs, you'd have boxes flying off the end, things moving at 50 miles an hour. You need that speed of that motor dialed back and controlled for what the actual application needs. But you also need 100 Newton meters of torque. You need a lot more twisting force to get that very long conveyor belt moving. Another example that we're going to focus on today, kind of just general air movement or fans. So typical high volume, low speed fans, spin those blades at about 100 revolutions per minute. Maybe need somewhere between 50 and 100 Newton meters of torque in order to spin those blades. In both of these very real scenarios, that motor that you bought at 1800 RPMs and 1 horsepower can't just plug on to these applications. You need to do something else in order to match up the speed and in order to match up the torque output of the machine. The way this is done today in almost every single application is really these 3 sorts of band-aids that you're putting on the outside of the motor. So first and foremost, if you got a motor and you're worried about how much temperature rise it's going to have and whether or not you're going to impact the life, you're going to implement a cooling strategy for the machine. That could be as simple as making sure that your motor is, 18 inches away from a wall, or maybe you put an extra fan blowing on the motor to keep it cool. In the most extreme examples, you will actually have a liquid cooling system that you will pump water or glycol around the motor in order to keep it cool. But in any case, you need to manage the thermal energy, so you have to implement some form of cooling strategy to make sure you don't burn the motors out. The second thing that is almost always done for motors is you need to go from 1800 revolutions per minute for the motor down to 200. So you're going to attach a gearbox, or you're going to attach some sort of belt pulley system in order to gear the motor down. So in order to get the speed down and the torque output up. And then lastly, and again, this is just the nature of all of us that are engineers, is you're going to upsize the motor because you want to add a factor of safety on top of it. So maybe you have a fan that needs 1 horsepower. Well, I'm going to buy a 2 horsepower machine. I'm gonna add, make the motor bigger so it doesn't run as quote unquote hard. I'll manage the thermal aspect that way, and I'll get longer life out of my machine. So these are the three ways that in practice, motors are actually designed and engineered into these various systems. A lot of what we hear from people that have industrial facilities or have commercial facilities, the first kind of myth is that, well, I'm already buying a super high efficient motor. Why is this a concern? I'm buying a motor right now that's already 85% efficiency. There's just not a lot of upside. What am I going to do? But again, your net efficiency for the system is not just the motor, but those other things that you have to do to enable the motor to work in the application. So, all right, we're going to add an active cooling system. In this case, maybe it's a secondary fan or some other sort of air movement directed over the machine. That 85% efficient motor now drops 1 point now down to 84%. Again, if I need 1 horsepower, well, 2 is probably better. I'm going to buy a 2 horsepower motor and put it on this machine. I'm going to run it at a lower loading factor, and I'm going to drop another 9 basis points off the efficiency of that motor. And then the real kicker is when you need to go from 1800, 2000 RPMs now down to 150, 200, 300 RPMs. Adding a gearbox, adding a belt pulley system can impact your motor efficiency anywhere from 10% to 40% reduction. In this case, we kind of split the difference and said, putting this 20-to-1 gearbox on here is going to take a 19% efficiency hit. And so by the time you get to the end and you look at your final system efficiency, the thing that you actually care about, the thing that you're actually paying your utility bill on, you have a final system efficiency anywhere from 50 to 60% net efficiency. So that, excuse me, that 85% efficient motor that you felt really good about when you started is actually not delivering that same sort of energy efficiency by the time you get it implemented into the system. You may be wondering, I wondered before coming into C-Motive, like, well, motors have to be getting more efficient, right? There's got to be people working on this. And it is true that traditional magnetic motors have gone up in efficiency over time, but they are starting to hit the limit of what can actually be achieved. So the first national standards for motor energy efficiency were released in 1992. And they spec'd that a motor, again, this same 1 horsepower size, very common in a lot of facilities, needed to have an efficiency of 72%. It took 15 years for the next threshold to be hit. And that, so from 1992 to 2007, the minimum efficiency standard went from 72 to 79%. 9 years after that, we went from 79% to 83%. 7 years later, and this right now has only been mandated in the EU. It will likely be coming to the United States in the next couple of years, is only a 3% efficiency premium over on top of that. So this extraordinary length of time has seen minimal amounts of efficiency gain over that period of time. So again, saying that you have an 85% efficient motor, it's not a stretch. That is state of the art today. And unfortunately, when you add on all those other accessories, it doesn't matter if you're buying a super premium efficiency motor, you're still hitting net efficiencies of 60%. So trying to tie this back to why people that, care about sustainability, why people that care about the bottom line, why do you care about motors in general? So to start with, probably well-known fact on everyone on the phone, not all electricity is the same. Whether your electricity mix comes from a mix of fossil fuels, whether it's heavily dominated by renewables, is going to impact what the carbon intensity of that kilowatt hour of electricity is, and obviously the cost as well. So we're going to focus on two examples here. So one, right here in Wisconsin, the carbon intensity of the electricity that is distributed here within the state is 566 kilos of carbon dioxide for every megawatt hour that's produced. And these numbers are from the EIA website that you can go look up as well. Electricity costs, and this is industrial electricity costs. This is not, unfortunately, what you and I pay at a residential level, is just over 7.5 cents per kilowatt hour. Now let's take this to another, kind of maybe a more extreme example, but Germany as a comparison. So Germany has about 40% less carbon intensity for every single megawatt hour that they produce, because their fuel mix is very different than what we have here in Wisconsin. And their electricity prices are significantly higher than we pay here right now, through a mix of different tariffs and just the costs of it. But well, that's way more than 5x, 4x, 6x. I have a hard time with math this morning. 5 to 6x higher electricity costs in an industrial facility in Germany than you have here in Wisconsin. If I take that same 1 horsepower motor and I say, I'm going to put it on a fan and I'm going to let it spin, 8,760 hours. So the entirety of the year. Here in Wisconsin, running that 1 horsepower fan for a full year would cost you $830 in electricity cost. And it would be responsible for 6,200 kilos of emitted carbon from that electricity. That exact same fan running the exact same amount of time in Germany would cost over $4,600 to operate, and have a carbon footprint of 3,500 kilos. So again, very different. And you can kind of look at these numbers and understand why in Europe, why in the Northeast of the United States, down in California, you would be much more interested in energy efficiency than maybe you would be here in Wisconsin. So a little bit about us and how we are trying to help people address this problem. So again, C-Motive, we're a technology that came out of UW-Madison. And we are the world's only company that is commercializing electrostatic motor technology. Electrostatic motors, a lot of animations here. Very different from the magnetic machines that, again, 99.9% of motors that you deal with today are magnetic motors. Electrostatic motors use a different fundamental physics in order to do that energy conversion from electricity to mechanical power. So just like I had the example of the battery with the copper wire, the way an electrostatic motor works is like if you took a balloon and you rubbed it against hair or a wool sweater, you can feel the electric field, that static electricity on the surface of the balloon. That is the force that we're using inside of our motors, just scaled up tens of thousands of times. Ben Franklin originally came up with this design 275 years ago, but obviously didn't have the benefits of modern material science, did not have modern power electronics as well. So what he was able to demonstrate was in this simple system he had here, he had two Leyden jars. One was positively charged, the other was negatively charged. And this spindle with a bunch of metal thimbles on the end of it, what he was able to show was that static electricity, you can create enough attractive and repulsive forces in order to spin that spindle around. It was an interesting science fair experiment, but it couldn't create enough power to actually be usable to anybody in the marketplace. This technology and this idea just got put on the shelf for 150 years before the next academic picked it up, realized that they weren't quite there yet, and it got put on the shelf again. That process repeated itself until Dan and Justin took a look at this while they were getting their degrees at UW-Madison and thought, hey, what if we thought about this entirely differently? What if we thought about this at a system level? What if we moved from, metal thimbles and glass rods to printed circuit boards for the inside of the machine? What if we tried to co-optimize the mechanical design of it, the electrical topology of it? And this is where we're at today. So this cutaway of this machine here on the right, this is what we're producing in our labs here in Middleton, Wisconsin, directly going after some of these applications that we've talked about. Going all the way back to the beginning, where we talked about heat being the biggest enemy of traditional electromagnetic motors, heat being the single largest source of efficiency loss. What we're doing here in this experiment, so this is a top-down picture of electrostatic motor on the left, that same 1 horsepower traditional magnetic machine on the right, and they're basically doing a little tug of war here between the two of the motors. So they're both spinning at the same amount of torque. And after an hour, we took a thermal camera image of the two machines from the top. And obviously, it's pretty easy to see that the traditional motor, just like you saw in the other image earlier, warmed from 20 degrees centigrade up to 45 degrees centigrade in the course of an hour. The electrostatic machine remained the same temperature. And this is, again, because in our motor, we don't have copper windings. We're not passing a lot of electricity flowing through copper. There's nowhere for that heat to be generated as compared to the traditional motor. Another aspect that I've not talked about, because again, we've been focusing on the energy efficiency, but worth noting is that not all products are created the same in terms of the raw materials that go into them. So traditional magnetic motors, up to 20% of the weight of the motor can be copper. Up to 40% can be electrical steel. And in some cases, you can have as high as 10% of permanent magnets in the motor. Again, just because we're starting from fundamentally different physics, The only copper we have in our machine is the copper that's on the traces of our printed circuit boards. There is no other copper windings. We do not have any electrical steel. There's no permanent magnets to be had. So one of the things that we're also investigating right now is really the embodied carbon content of the different types of motors, because we know that a lot of people, not just interested in emitted carbon from scope 2 emissions, but also the embodied carbon of the products that are in their facilities. Practically speaking, there's a very strong supply chain aspect to this differentiation between magnetic and electrostatic machines as well. So everyone, I'm sure, has been very aware of commodity prices and how they've gone up over the past 2 or 3 years, but very specifically, copper has been up almost 60%, electrical steel up over 70%, and permanent magnets have well more than doubled in price. That's a worry if you're a motor manufacturer, or if you have a facility where you have 100, 1,000, 5,000 motors in them. They're going to cost you more upfront. Even more concerning is availability of these critical materials. So in almost all cases, the vast majority of these materials are not sourced in the United States. They are not sourced in Europe or South America. Almost all of these materials are mined, refined, and produced in China. There continue to be concerns, obviously, about whether or not we're going to be able to procure these critical raw materials from international suppliers. And motor manufacturers are struggling with this right now. The cost of motors has more than doubled in the past few years, not just because of the raw material prices going up, but also people hedging their bets on whether or not they're going to be able to procure the necessary raw materials for efficient motors in the future. So bringing all of this back to carbon savings and cost savings, when we look at what an electrostatic machine would deliver, again, same application, it's a 1 horsepower fan, it's running 100% of the hours of a year. The carbon intensity from an electrostatic machine would be 2,200 kilos of CO2, or 65% savings over the traditional motor, 1,200 kilos of CO2 in Germany, and just as importantly, equivalent amount of dollar savings. So that $800 or $810 it took to run that fan here in Wisconsin the full year round is now down to 500 some odd dollars. In Germany, that delta is obviously much bigger because the cost of electricity is so much more. This is, we think, kind of a no-brainer for a lot of people that use a lot of motors in their facility. I'm not going to go through these here. If you're interested in these details, reach out to Rachel or I. We have 2 example case studies. Again, focus on a logistics facility and agricultural fans. But what we do is we go through the numbers in a bit more detail and aggregate them up to show just how big these savings are. So, maybe you don't have a logistics facility where you have 1,000 motors in it, but the U.S. Postal Service does, FedEx, Amazon, Walmart, Chewy.com, right? Pick your company that's moving a lot of boxes. These are very big numbers and they're very real for people. So just to wrap up, because I'm sure people are sick of hearing me prattle on. So here's where we're at as a company. So we are in that transitionary phase from we've done the research, we've done the development, we've proven the science. We are looking for early adopter partners. We are looking for forward-looking companies right here in Wisconsin that see the need for both carbon savings as well as electricity savings, and would be interested and willing to do demo projects with us. That could be putting one of these motors on some fans that you have in your facility. It could be looking at other operations like pumps or compressors or conveyor systems. We've got obviously specs for the motor, and we'd be more than happy to talk about this with people. But we're looking for people that are interested in those cost savings and those carbon savings, and how we might be able to partner up and to help. So that's kind of the introduction. That's what we want to talk about. So again, happy to answer any questions at all.
Well, thanks so much, Matt. I love these webinars because even I learned so much. Not coming from a very technical background, it was very easy to understand information. And so we do have one question here, and I do want to invite folks, if you have questions, please to either chime in. You can raise your hand, you can speak up, or type it in the chat. But Sandy is asking if you are testing for EMC, effectively communicating the EMC message in design teams.
So I had to open the link just to make sure that, and I'm hoping that EMC stands for electromagnetic compatibility. And if not, please correct me.
Yeah,
but
Sandy, speak up. Yeah.
Two interesting things about the motor that we're building right now. So one, it is audibly quiet because there's with no gearbox. Typically you hear the whining out of motors when they're spinning up. So this is an audibly quiet machine. It's also electromagnetic noise quiet too. And that's again, because there's no electric field spinning around inside of the motor. So it, for a lot of applications where you're in a critical environment where you can't have a bunch of EMC noise or EMF noise, that is not as much or at all a concern with an electrostatic motor. We have not done like full, full-fledged testing and had it verified by a third-party source, but we'll be happy to talk about that and explain what we have done in our labs and see if there's, again, if that's something that you have the capability of doing or interested, I'd be happy to talk about demos for that. Great.
Another question, what is a typical motor horsepower?
So our initial family of motors that we'll be producing will be between 1 and 3 horsepower. Right now we're at the lower end because, again, venture-backed startup company, we're trying to minimize our costs as much as possible. So we're building small machines now. That's what we're looking for the demo opportunities. But in order for us to increase the power rating of the motor, from a 1 horsepower to a 3 horsepower motor, the length of the machine will get longer by like an inch or 2. So it's pretty easy for us to go up in power rating.
Makes sense. A question about motors speed controllability.
Yep.
Are you using technology for speed control?
Yeah. So our motors are both speed and torque control. So you could either set the dial, say, hey, I want this thing to run at 100 RPMs, and it'll make sure that it centers itself around there. Or if there's a torque setting that needs to be done, we're doing both of those. So our motors operate. Most people are used to using like a variable frequency drive in order to be able to tweak and dial in for the most amount of energy savings. We're doing the same thing on our motor. So it's not just one speed, but anywhere from 0 to 500 RPM settable.
I love these technical questions. You're just on it. What is your drive operating frequency?
Yeah. So you set me up to be on the technical questions, and I gotta admit, I don't have the answer to this one at all. This is one we're gonna have to take back to someone way smarter than me to be able to get an accurate answer on that one.
All right, great. Any other questions from folks? Interest? Okay, one more came in here.
Yeah.
Your motors are currently. Oh, go ahead.
Oh, sorry, go ahead. Sorry.
I was just going to read this question. Your motors are currently 120 vac and 240 vac single phase. Are they being tested with VFDs?
Yeah. So our motors are, so we are also building the drive. I didn't talk at all about this in here. The drive is simply the power electronics that sit between the wall socket and the motor. You need the drive to be able to tell the motor what to do and everything else. So right now for our first demo units, these 1 horsepower motors, the drive plugs into a standard 120 volts, 60 hertz single phase wall outlet. I could take the thing home and spin it in my living room if I wanted to. In the future, we're looking at those kind of like standard industrial voltages. So 120, 480 volt 3-phase, that's where we're centering our development around. And then to answer the question above, do the motors run on alternating or direct current? So obviously from the wall into the drive, it's alternating current going in there. But if we want to get a little bit more detailed. So what happens between our drive and our motor is that we put voltage on DC voltage on the rotors, the rotating plates, and we put an AC voltage on the stators. And as that alternating current wave moves around our stators, the rotors get dragged along with it. So the actual answer is for like the motor itself, it actually runs on both AC and DC, even though, you know, you only need to provide AC from the wall. If that made sense.
Yeah.
To Rachel to verify that made sense.
I gotcha. Well, great. I mean,
Awesome.
yeah, any other questions, or just, I'm assuming the best way to follow up if folks are interested is to just reach out directly to you. I know
Yeah.
you've already got some folks that have reached out.
And again, we really do, we are happy to answer questions about traditional motors. I'd be happy to share some of the calculators we have so you can see it for yourself. You know, if you've got a facility, you know, you've got 100 motors running, you know, we can go through and help you do just a rudimentary analysis of like, hey, here's how much money I'm probably wasting on these motors the way they are today. So happy to answer questions about, you know, maybe what you're doing now, obviously more questions about what we're doing. And then if there is interest in learning more or talking about a demo or even just coming and visiting and seeing for yourself, please just email Rachel or I and we'll set something up.
Fantastic. And
Awesome.
I would just say that keep us in the loop, keep WSCC in the loop as this goes, because it'd be fun to just maybe follow up, you know, do a follow up to this and how the process is going and when you're, you know, how the demos go and, you know, if more people might be interested at that time. So I'd love to do that.
Yeah, we'd love to find a demo and then come back and do one of these with actual results, right? So here's,
Exactly.
you know, right here's how WSBC members are working together and actually tangible results from these new technologies. So we'll definitely keep you in the loop.
Fantastic.
Cool.
Great. Well, thank you so much for your time. I look forward to following up, and I will share out the recording as well as the contact information if you didn't get a chance to grab that. So thanks everyone for your time, and we'll be in touch.
Thank you.